All right, good morning. The first lecture today would be about Stellar and Monero, which are two additional cryptocurrencies. So what are Stellar and Monero? They are both in the top 20. And Stellar is based on the paper and ideas from Stanford. The paper is called the Stellar Consensus Protocol, a federated model for internet-level consensus. While Monero is a rare bird in the sense that it's not coming from academia. It's one of the few cryptocurrencies where essentially it's the even, well, no one knows if Satoshi Nakamoto is from academia, but for some of the cryptocurrencies, basically they were driven by individuals with the technical knowledge, but without emphasis on the academic analysis. Okay, so before we start talking about Stellar, we need a bit of background about quorums. So yesterday, you saw a bit of some quorum applications. We were talking about majority. In the context of Paxos, we were talking about majority of acceptors. So the concept of majority can be generalized. Majority is just one specific case for quorums. So what is a quorum? So normally all nodes need to confirm their consent. However, what if some nodes are faulty or slow to respond? That's the motivation for using quorums. And the idea is as following. So for majority, like here it's written in the specific case of majority, so only majority need to confirm, the remaining minority will follow. So how do we generalize it? A quorum system Q is a set of pairwise overlapping sets of nodes such that if there is a set S that belongs to a quorum system such that all nodes in S confirm their consents, this will be enough, right? So we need only one set out of a set of sets, and we need all nodes in that set to confirm. And the other rule is that there could be no two sets belonging to Q to the set of sets, such that nodes in the two sets confirm different values. So usually, one could say that a quorum is a set of overlapping sets, pairwise overlapping. So imagine that a quorum would contain 10 different sets. We need a sets of nodes. We need a consent from all nodes in one set. But every set among those 10 would be overlapping with every other set within those 10. Okay, so quorums, in most applications, quorums are determined and announced a priori. They are not formed dynamically. So beforehand, we know all about Q and all about different sets that belong to Q. And of course, this approach requires static membership in the system without any dynamic changes, because if nodes can fail and leave the system, while other nodes will be joining the system, which is called churn, by the way, in the computer science terminology. So if we have churn, then we need to update the quorum sets. So the static approach, which is widely used in classic, like was widely used in the 90s, for example, and even maybe 20 years ago, so that doesn't work. Okay, so what does Stellar do with quorums? Stellar introduces the concept of federated quorums. So it creates quorums dynamically, so that each node has a set of nodes. Each node V has a set SV of nodes that V trusts. And V proposes to use a subset of SV as a quorum. For example, 3/4 of SV. And in the Stellar terminology, it's called a quorum slice of V. So each node expresses its desire, specifies the other nodes that this node trusts, and those nodes would constitute the quorum for that node. And different nodes, of course, would propose different slices. And a quorum is a set of nodes that contains a slice for each of its members. Here's an example. So in this example, we have 4 nodes. Sorry, I don't know why it came out a bit blurred. But okay, but I hope it's visible. In this example, there are 4 nodes, V1 to V4. The slices are as following. The slice for V1 is V1, V2, V3, and the slice for V2, the slice for V3, and the slice for V4 is V2, V3, V4. In this case, the quorum would need to include all 4 nodes. Let's take a look at another example. Here we have 10 nodes, and they are divided as following. The first 4 nodes want a slice out of V2, V3, V4, including itself, right? So that's the rule. So V2 would want V2 and 2 additional nodes from this subset. Then we have like the middle tier. In here for these nodes, V5 to V8, the slice would be the node itself plus any 2 additional top tier nodes. So a slice for V6 would be V6 and 2 nodes from here. And then we have a left here, 2 additional nodes. The slice for a node here would be node itself plus 2 additional middle tier nodes. So then we combine, so what would be a quorum? In this case, well, as a matter of fact, the quorum in this case, the quorum in this case would still be like all the nodes, which is not beneficial, because every node wants to include itself. But it's also possible for a slice not to include the node itself, right? Or to include, or it could be. It could be like here, slice is 3 out of 4 nodes, and if it doesn't need to include itself, then this way we can the size of the quorum on a large-scale system can be significantly smaller than the size of the system itself, which is the point. So the idea of Stellar is to build dynamic federated quorums on the fly. Once the quorum is determined, Stellar executes what's called a federated voting, which is a 3-phase protocol. So it's similar to many other BFT protocols. It includes 3 phases, not 2 phases like Paxos. And in this protocol, this protocol, I mean, the main purpose, of course, is to reach consensus. So a node may nominate a particular value multiple times, or it may actually nominate different values, like change the vote and vote for different values. So that's the first stage. In the second stage, a node would confirm a single value, would commit to a single value. Like in this example, this is the state diagram for one particular node. So initially the node is then committed, and then the node would be voting for two different values. And then there would be an exchange with the other nodes, and based on the exchange, the node would see which value is the majority and commit to that value by accepting the value. So it may vote for A and A tag, but it would only accept A. And then there is a quorum in parallel to this process. There is a quorum discovery, because initially a node doesn't know what a quorum is and from whom there is a need to collect the votes. Quorums are dynamic and built on the fly. So in parallel, by this stage, a node would do the constitution. And at this point, a node can detect that there is a quorum which accepts this value. As soon as a node learns that there is a quorum which has accepted the value, at this point it would confirm. And then it can proceed with the next instance of consensus. So if there are failures, and again we are also talking about crash, but also about Byzantine failures, then confirming may take several communication rounds. Yeah, I should also mention that after the value is accepted, the node would stop voting. So the protocol, the specific protocol of Stellar is actually very, very complicated. And that's because of different rules, how to build quorums, and when the quorum may accept the value and when the quorum may not accept the value. So, so over at least 5 years, there have been many papers, a lot of research on the exact semantics of the consensus protocol in Stellar. It's one of the most complicated protocols among cryptocurrencies. So I'm not going into details. I'm just giving a high-level overview. One very interesting property of consensus in Stellar is individual liveness. What does it mean? I mean, usually in consensus protocols, you want agreement, the safety property, meaning no safety property means no two good processes, honest processes would ever disagree with each other, would ever produce different values. And we want liveness. Liveness means that every honest node would eventually produce a value. So in most consensus protocols, the liveness is universal, right? So the protocol moves forward as a whole. If one node can proceed with consensus and another node, one honest node can proceed with consensus, then another honest node may proceed with consensus. It never happens in most consensus protocols that only a subset of honest nodes proceed. In Stellar, the situation is different because of the individual quorum rules. So let's come back to this example. It's the same example we saw previously. Now imagine that all nodes here failed. What happens in this case? Well, these nodes may still proceed with consensus and confirm and accept values, because they need a slice of 3 out of this subset, and this subset is perfectly functioning. So as a result, the subset would have liveness provided to them. They would make progress on consensus. On the other hand, the nodes in this subset, also the nodes in this subset, would not have liveness provided to them. And therefore, a very unique characteristic of Stellar is that liveness is individual and not global for the entire system. There are some interesting additional tidbits about Stellar. So how a quorum discovered during voting? Upon nominating a value, a node also sends information about its quorum slices. And again, to get confirmed, the value needs to be confirmed by one slice from each node. Sorry for the typo, it's not slide, it's slice from each node. So that's interesting, right? So a node sends information about its quorum slice together with the value it votes for. And then everyone would need to calculate the union of different slices. And that's done on the fly. And again, the rules are quite complicated about Stellar approaches, the dynamic calculation, the union, because some nodes may be Byzantine and may be sending some totally arbitrary slices. The Stellar system has additional optimizations. For example, if deployed at a large scale, then sets of nodes would elect a representative. So again, it's very similar to committee selection in Algorand. And then only the committee would send slices. So the committee selection is similar to Algorand, but in Algorand, the committee proposes a block. In Stellar, the committee nodes in the committee would send slices. So how does Stellar compare with alternative approaches? So here the mechanisms are proof of work, proof of stake, Byzantine Agreement Protocol, and Stellar Consensus Protocol. And the dimensions of comparison are as follows. Decentralized control over quorum. Is quorum determined in a centralized way or in a decentralized way? How high or low is the latency of the protocol? How flexible are the trust assumptions in the protocol? And what level of, there are certain security guarantees, but they're probably less relevant for us. Okay, so decentralized control. Proof of work, such as the mechanism in Bitcoin, provides total decentralized control, so there is no centralization. The same about proof of stake. However, for classical Byzantine agreement, like Paxos, someone needs to configure the quorums a priori, beforehand. In which case, you don't get any decentralized control and flexibility over the constitution of quorum. And this is where the consensus is stellar, basically making the most contribution. It's also low latency, so it's similar to normal Byzantine agreement and much lower than proof of work. And it also provides flexible trust configuration. So that was the short overview of Stellar. Now I'm proceeding to the second system, which is called Monero. What's the motivation? So Monero is totally different from Stellar. So we just combine them together, like package them together in a single lecture, but they are totally different beasts. All right, so what's the motivation for Monero? Monero is similar to Bitcoin, but with some additional privacy-related guarantees. So why is the creator of Monero was dissatisfied with Bitcoin? Well, transactions in Bitcoin can be traced. What exactly does it mean? Well, for each input, we can build. We know where we know the output, which connects to this input. The same UTXO, right? So we have a UTXO here, and then we use it as the input in another transaction. So this way we can build, first of all, a graph of transactions. And everyone would be able to see this graph is publicly available for everyone, not just to the parties involved in a particular transaction. And this graph is undesirable even when participants are represented by public keys and not by real identities. Because, for example, the sender of a particular, like the receiver of the transaction would usually know the sender of the transaction along with her public key. And therefore, like, two different senders can collude and learn more about the entity, the sender of transaction B. And okay, another example. If the transaction is very large, meaning it has a lot of inputs and a lot of outputs, then most likely this transaction belongs to some bulk user, not an individual user, perhaps a crypto exchange. So this way, by looking at the graph, we can understand certain things. And that is undesirable in terms of privacy. All right, so what Monero was set to solve was the problem of transaction traceability. And the two properties that Monero wanted to guarantee were sender untraceability and receiver unlinkability. What is sender untraceability? Given a transaction, there is a set of equiprobable senders, meaning, well, I'm going to demonstrate what it means on the next slide. So, sender untraceability implies sender unlinkability, which is the property that given to transactions, we cannot say if they were sent by the same sender. It also implies that given to transaction, we cannot say if the receiver of the first is the sender of the second. And therefore, we cannot build a graph of transactions the way we did in Bitcoin. The second property is receiver unlinkability, which means that given to transactions, it's computationally infeasible, hard, to determine if they were sent to the same receiver. So those are nice properties in terms of privacy. But of course, the main challenge is how we can guarantee those properties alongside with checking, alongside with defending against double spending, for example. Okay, let's take a look at the example. In Monero, an input has multiple pair transactions, of which one is real and the rest are fake. And for the fake transaction, they use the term of mix-ins. So you see here in transaction B is linked not with just one output, but in this example with 3 different outputs, of which one is real and the other 2 is fake. But from the outside, we don't know which one is the real one. And this is the way to achieve untraceability of the sender. How is this property achieved in Monero? The answer is that they use yet another cryptographic primitive, which is called ring signatures. So in Bitcoin, Alice, when Alice sends a transaction, she signs it with her private key and a public key of the receiver, to make sure that only the receiver can decode the transaction, can receive the funds using the receiver's private key, okay? Now, in Monero it's different. With ring signatures, Alice, the sender, picks an anonymity group, which consists, say, of four senders, Bob, Carol, Derek, and Eve, and then Alice signs the message in a very interesting way. She signs the message with her private key and the public key of Alice, Bob, Carol, Derek, and Eve. Now, what ring signature gives us is that everyone can see that the sender is within the group. So, without having a private key, it's not possible to build a ring signature. However, which sender from the group is equiprobable? And thus nobody can see that can determine that the sender is Alice. The receiver may possess this information, though, because, like, for example, you purchase goods from Amazon.com, you know this, and okay, so Amazon.com would know that it's you, or at least may know that it's you. However, so it's not complete untraceability, but it's much more limited. It's not open to the entire world to see the graph of transactions. So is it clear how ring signatures work? Well, I have not explained how you build the ring signatures, but how they are used to achieve untraceability. So again, we have a group of senders, and any sender from the group can use his or her private signature along with the his or her private key, along with the public keys of all senders, all nodes within the group. And that's a ring signature. And then everyone could see, everyone from outside the group could see that it's signed, the message is signed by the group, but no one knows by whom within the group. So this is how untraceability is achieved, but as mentioned, sender untraceability complicates detection of double spending. Because now, the same token can be legitimately used as an input in multiple transactions. But only once it will be the real token. In other cases, it would be a mixing. It would be fake. But still, from the outside, it looks like double spending, right? The same token, the same output is used as the input to multiple transactions, and that's valid, unlike Bitcoin. Okay, so how do we know that it's double spending in this case? So in order to provide defense protection against double spending, Monero uses the concept of a one-time ring signature. It's a modification of the typical ring signature. And in one-time ring signature, each private key can be used only once for the same token. Okay, so what happens if the private key is used more than once for the same token? I mean, that would be a double spending, of course. The real problem, like, when does double spending occur in Monero? When the same token is used not as a mixing, but as a real value, as a real input to multiple transactions. And in order to achieve that, the double spender would need to use the secret key on the same token. And this is what Monero prevents. So what happens if the same private key is used twice on the same token? In this case, the one-time ring signature mechanism deliberately breaks sender untraceability. And this way, everyone will be able to see that it's the same sender in both cases. So it's quite an interesting extension of the ring signature mechanism. So, of course, the scheme weakens untraceability for the sake of protection against double spending, but there is a bit of a trade-off. Okay, so that was about sender untraceability. What about the receiver side? What about receiver unlinkability? So Monero achieves receiver unlinkability in the following way. The sender produces a one-time address of the receiver, using the public key of the receiver and the private key of the sender. So it's very interesting because in Bitcoin, it's the receiver who produces the receiver address, not the sender. That's natural. I mean, usually when I ask someone to transfer me money, I'm supposed to give the bank account information. But in this case, in Monero, it's the sender who determines the address of the receiver. So the sender produces a one-time address of the receiver. And okay, so how does the receiver even know that it's the other, like I'm the receiver? How do I even know that this is my address and that the transaction is intended for me? In order to achieve that, the receiver can detect that the transfer is to her using her private key. So the receiver is supposed to continually scan all new transactions in the ledger. And then, using the private key, she would be able to detect that this is her, that this particular transfer is intended for her. Of course, continuously scanning all transactions can be quite an expensive operation for the receiver. All right. So what's the perception and criticism of Monero? Monero provides very nice properties with respect to privacy, but they do come at a cost. The first issue is that more mix-ins means bigger transactions, and for bigger transactions, you need to usually pay higher fees to the miner. Therefore, the fees, like transactions, are more expensive in Monero compared to Bitcoin. Okay, second issue. If the use of mix-ins in a transaction is essentially at the discretion of a sender, how many mix-ins should I use? Well, Monero doesn't want to dictate the number of mix-ins because the sender would need to pay higher fees, right? So the sender can select to use 5 mix-ins, can select to use 20 mix-ins, or can select to not to use mix-ins at all. 0 mix-ins, also possible, at the discretion of the sender. But herein lies a problem. Imagine that there is a sender which, okay, sorry, I said transaction B. It was actually the sender of transaction A which made this choice, not the receiver of transaction B. But now look at transaction C. The sender of transaction C decided to use 1 mix-in. And it happened to be exactly the same No, okay, sorry. What I said was a bit incorrect. So the sender, the problem here is with transaction C. In transaction C, the sender decided not to use any mix-ins. And therefore, this input has only one corresponding output, and that there is no ring here. There are no mix-ins for this one, okay? So the sender of transaction C decided to break traceability for itself. However, it also creates a problem for transaction A, because the sender of transaction A decided to use 1 mix-in, which happened to be exactly this output. However, now everyone knows that this output corresponds to this input, so it cannot correspond to this output. And by realizing this, we can come to the conclusion that this input corresponds to this output, and this mix-in doesn't help at all. So, sorry for the confusion. I hope the example is understandable now. And this is just one scenario. It turns out that the untraceability can still be broken in a number of other scenarios as well. For example, by using the value analysis. The value of the transfers are still in plain text for everyone to see, and therefore we can check the values, and the sum of the inputs must be equal to the sum of the outputs in every transaction. And by using this rule, it may still be possible to break down transferability. And we previously talked about attacks such as double spending. Double spending is protected against by disclosing the sender. But if we disclose the sender, we may break traceability not just for that sender, but we may compromise the entire graph. Therefore, the protection in Monero is still considered to be relatively fragile, despite all the nice ideas. So that's the end of the lecture, and I will be happy to take additional questions. A blockchain, sorry, what is public or private? What happens? Transaction? I'm trying to fully understand. Like I understand what you are saying, but I still trying to grasp the entire scenario, right? So yes, in Monero there are there are blocks like the same as and there is mining. So in that sense, it's the same as Bitcoin. Yes. So who is responsible for what operation? So which operation are you looking the responsible party for? Okay, so that's not specific to, your question is not specific to Monero, right? I mean, you could ask the same question about Bitcoin, right? What happens if by you are saying it's the mistake of the sender, right? So the sender by mistake send the coin to a different user. There is no protection against that. Like it's many things in Bitcoin are irreversible. Some theft of coins is also can also be irreversible. So I mean I can talk about two specific cases, like in which I was a bit involved, and it happened in Norway. So there was a billionaire, he's still a billionaire, whose wife disappeared, and which was very strange. I mean, how someone could kidnap the wife. But anyway, the kidnappers asked him to pay a ransom in Bitcoin. So when he did it, the police was already involved, and so they tried to trace the transaction. Despite all that, sort of the kidnappers managed to disappear somewhere, like Caribbean islands, like the other part of the globe. So the police invoked Interpol. Interpol has been searching for those funds for 3 years. At the end, they gave up. So this is the extent to which like the operations are irreversible and fragile in Bitcoin. I'm signing with well, when I'm signing something with the private key and I give the signature, I disclose my private key. I only disclose the signature.
But other signatures are also included to bring the anonymity, right?
It's interesting. It's a single signature. No, it's an operation which takes multiple keys and produces a single signature.
How that exactly works with one?
So now what happened? Okay, so how do we know that it's correct signature? Anyone can take the public keys of all participants in the anonymity group and just by using the public keys confirm that this is a signature. But using only public keys, it's impossible to produce the signature. In order to produce the signature, someone needs to use at least one private key from the group.
That this is the right transaction.
What do you mean right? Right in what sense? What verification of what?
Receiver will come to know that this is the valid transaction.
That it's a valid transaction because well, it's a valid transaction because of this property that the same private key can be used on the same token only once.
Right.
So this is how they know because if the same private key is used twice, then the identity would be disclosed.
Like if we go for the anonymity, then how we will prove that this is a valid transaction? And if we are proving that this is a valid transaction, then how will we will maintain the anonymity? That's my doubt.
Well, as long as it's not used the second time, the anonymity is maintained. So we can check that the identity, like the identity of the sender is disclosed. Of course.
In Stellar, you told that the quorum, what they are selecting to participate in consensus. So, are they selected randomly, or is there any parameter that to be selecting the quorum? Randomly, each node will propose.
No, it's not random. It's all policy, like.
So, what is the parameter?
Okay, I can say it's like in politics, right? I can say I trust that organization, but I don't trust, say, another party, another political party, or another organization. I trust my friends, like in the social network. So every node decides for the node represents a person, okay?
So, each node
So the person decides for himself or herself whom to trust.
so each node will maintain a trust parameter. Based on that, other nodes will do the quorum.
Exactly. That's the whole point. Each node autonomously determines its trust.
Worst case, if every node selects itself, then there will be no quorum.
Then it's a problem. So in the world, like there are rules to be enforced, right? So if every node selects itself, then the quorum would need to contain everyone in the system, which defeats the purpose of quorums. So that's not a good situation.
How to resolve that situation? It will keep on going in infinity loop.
Well, I mean, it's a good question. I guess one could say that there is an incentive to avoid this situation, right? Because like everyone understands, if I pick myself, then everyone would do the same, and then the system would not be operational, right? And there is an incentive to make the system operational. So this is why there are certain recommendations how to select your quorum, your slice, okay? In Stellar terminology is the slice. So there are recommendations how to do it in a good way.
What are those recommendations?
Those recommendations would be like a certain number. So for example, like slices should not be too small because that would be too limiting, right? Like if you select, for example, just one of your friends, then what happens if this friend crashes, right? It's a problem. So the slices shouldn't be too small. On the other hand, if you make your slice too big, then again everyone would need or too big or select nodes which you do not overlap with other slices like yourself, then it results in a very large quorum at the end. So you need to maintain the balance. Also, you need to bake in some flexibility. What do I mean by flexibility? A good policy would be 3/4 of a given set. So it's not, you need to be a bit flexible, right? You do not say, okay, I need vote from this, and this, from very specific nodes. Say, I would be happy to get 3/4 of the votes from this set. And this way you can tolerate failures of some of the nodes within the set or temporary disconnections. There are more rules, but again, Stellar is one of the most complicated systems among cryptocurrencies.
Five minutes break now.
Okay, let us start with the next lecture, which should be about the cryptocurrency of Zcash, and which would Zcash is based on the technique of ZK snarks. So we also talk about zero knowledge snarks, and we'll also talk about POW, which is different than the classical crypto puzzles of Bitcoin. So the use of zero knowledge in blockchain is typically based on non-interactive zero knowledge. So the examples in the tutorial and the lecture on zero knowledge, we mostly looked at the interactive zero knowledge, where there were several rounds of interaction between the prover and the verifier. However, it doesn't have to be. There are also flavors of zero knowledge without interaction. Such flavors of zero knowledge is called one-shot ZKP. So what is one-shot ZKP? It means that the prover stores something, for example, on blockchain, and the verifier can verify it without any interaction with the prover, just based on the proof stored on blockchain. And indeed, it's particularly suitable for blockchains where transactions are verified by individual nodes and there is no central authority to oversee the verification process. And usually there is no channel between whoever put the information on the ledger and whoever verifies the ledger. There's no communication channel. So the idea of non-interactive ZKPs comes from the seminal result of 1988, that actually a common string shared between the prover and the verifier is sufficient to achieve computational zero knowledge without requiring interaction. So there must be some shared string. Okay, so how do you sort of sneak this shared string in? Can you just store it on blockchain? Do you need some other ways to do it? And this question gives rise to actually to different techniques to provide non-interactive zero knowledge. So if impossibility results, so for example, impossibility result that without such a string it's impossible to achieve such a zero knowledge. So such impossibility results have eventually led to multiple solutions with different trade-offs. And as of today, there are three most popular proof systems for non-interactive zero knowledge which are used in the context of blockchain. They are called ZK snarks, ZK starks, and bullet proofs. How do we compare between the three? So what do we want? We want the sort of the computation for the prover, the production of the zero knowledge to be fast. We want the verification to be fast, and we want the size of the proof to be small because it needs to be stored on blockchain. So those are the three desirable properties for non-interactive zero knowledge proofs: the speed of producing the proof, the size of the proof, and the speed of the verification. And herein lies the trade-off. You can see that bullet proofs, they're probably the worst of the bunch. They have the slowest proof production speed in the order of 30 seconds. They have the slowest verification speed in the order of 1,100 milliseconds. And the size of the proof is in the order of small number of kilobytes. So it's medium. Then we have ZK snarks, which are very fast to produce proofs, the fastest to verify, and the smallest in terms of size. And in ZK Starks, the production of the proof is even faster, but the difference is not big. The verification is also very fast, just a bit slower. However, the size of the proof is quite big, maybe prohibitively big, for it to use in blockchain. Because of this, ZK Snarks is the most common technique to use in blockchain. What's the catch? The catch is that it requires more setup than the other techniques. So more configuration. So that's basically the idea of zero knowledge proofs, the implementation of zero knowledge proofs in the context of blockchain. Okay, so that's like a background behind Zcash. Now let's move to discussing Zcash. What's the motivation? What was the criticism? Why did the authors of Zcash thought it would be a good idea to come out with Zcash? What was their criticism of Bitcoin? Well, they said that anonymization in Bitcoin was not enough. Bitcoin can be, there are several reasons why, or there are several things which can help the attacker trace transactions. First, there is the graph of transaction, so it's the same criticism as in Monero, but it goes further. They also say the transfer values are in plain text. So if we see, for example, that there is some very weird amount of, like 239, for example, Bitcoins is transferred in one transaction, and then even if we hide the trace, we see another transaction which uses 239 Bitcoins. Well, that's an unusual value. And if it's used in both transactions, there's high suspicion that both transactions are connected. And there is a third element which helps the attacker, and that's transaction dates. So transactions in Bitcoin, significant amount of Bitcoins are spent very fast after they're being transferred, right? So we can correlate transaction also based on the timing. So those are the three factors that sort of motivated them to think about Zcash. Okay, so they had an inspiration. They were looking at cryptocurrency exchanges. You know that. So what cryptocurrency exchanges do? They have high volume of transactions, so they take, like they store wallets for many customers, and then they facilitate operation using nice graphical interface and other facilities. And like the idea of crypto exchange, if it's a big crypto exchange, that maybe some trade can be done internally without even going to Bitcoin, right? Between two users of the same crypto exchange. So so those crypto exchanges usually do bulk operations. So because they do bulk operations, it helps obfuscate the history. Right? Because imagine that you take like 5 different transactions and you batch them together in a single transaction. So now instead of you had one transaction, so Alice was transferring to Bob, Carol was transferring to Derek, and Eve was transferring to Oscar. Okay? 3 transactions, but could be many such transactions. Now instead of 3 transactions, we have a single transaction. So what crypto exchange does, it batches the transaction, instead produce single transaction. which takes inputs from Alice, Carol, and Eve, and transfer funds to say to three others. So this batching helps with obfuscation, right? Because now it's more difficult to understand who transferred to whom. Now we have three inputs, three outputs. How do they correlate with each other? That helps obfuscation. So that was their idea. It also, another reason why cryptocurrency exchanges help is that it introduces delays. So like one of the reasons for traceability is transaction times. But what crypto exchange can do, so it's batching. It means that like the crypto exchange would get the first transaction from Alice to Bob. It would not immediately put it in Bitcoin. Instead, it would wait for further transactions. So it would wait until it receives another transaction, for example, from Carol to Derek and from Eve to Oscar. And only after this delay, it would produce a batch, a single transaction, which is a batch of individual transactions. And this mode of operation introduces the delay. And this delay also helps with the obfuscation. What's the problem? So does it mean that crypto exchanges solve the problem? No, well, the problem is that security and privacy. Crypto exchanges are typically centralized and run by an operator, and that operator has access to all your data, right? So that part is not good in centralized crypto exchanges. Therefore, their idea was to come up with a decentralized crypto exchange, a decentralized mix, something similar to crypto exchanges, but without any centralized actor responsible for those operations. So how does it work? It employs one-shot zero-knowledge proofs to prevent transaction graphs analysis. So the proof is to show that the particular coin is valid. You do not reveal the source. You do not reveal the output, which is used as the input. You do not reveal it. But you prove that there is a correct output. However, zero coin doesn't hide the amount. And zero coin had a few additional problems. First of all, every token in zero coin has the same value, so you cannot transfer, like in Bitcoin, a single token may be many Bitcoins. In zero coin, a single token is always one unit of currency. So if you want to transfer a lot of currency, we need to have a lot of inputs, a lot of outputs, doesn't scale. And another problem with the zero coin was poor performance. So one proof was occupying order of 45 kilobytes of storage and was taking 1 second to verify. So not very fast. So then, pretty much the same authors came up with the idea of zero cache. Zero cache was like an evolution of zero coin. Zero cache hides denominations as well. So it not only mixes transactions, not only uses zero knowledge proofs, but it also hides how much. And it allows for anonymous transactions of variable amounts, right? So not just one unit of currency, arbitrary amount. And the proofs are taking only 1 kilobyte of storage instead of 45 kilobytes. And were taking 5 milliseconds to verify. So the performance was also much better. So this is what zero cache provides. But how does it work? Here's the basic idea of zero cache. So first of all, user needs to make a make a proof of funds. Zero cache also allows for interoperability, so it could be a certificate of deposit which allows a user to convert a specified number, for example, of bitcoins into the same number of zero coins. That would be a proof of funds. Okay, but now the real idea starts. In order to make a transfer, a user of zero coin creates a unique coin ID called serial number, SN. Next, the user creates a random secret, and then it creates what's called a coin commitment. Coin commitment is a one-way computation, which takes into account the random secret and the serial number of the coin, which again is supposed to be unique. And then the commitment is like a tuple, which consists of three elements. The commitment, the commitment is just a computation. Then the user creates a tuple, which consists of three elements: the commitment, the serial number, and the secret. And then the user would commit a transaction containing the commitment, but not the serial number or the secret, to the ledger. So the commitment is visible for all to see, but not the secret. And then how can another node spend that coin? It is spent by posting a transaction which would contain the serial number and the ZK snark proof of I know R, such that the commitment appears on the list of coin commitments. The list of coin commitment meaning in the ledger. So again, the sender, in order to spend the coin, the sender needs to post a transaction which would disclose. So previously there was just a commitment on the ledger. But in order to spend the coin, the sender needs also to disclose the serial number, but not the secret. The serial number and the proof, the zero knowledge proof of the fact that I, the sender, know the secret, such that the commitment appears on the ledger. So the list of, that's the basic idea. This is how you implement zero cache. And this is how the system works. Of course, on top of that basic ideas, they have many, many extensions and optimizations. For example, in the basic version, you store the commitment just on the ledger, in a list of commitments. And the commitments can be manifold, and the list may grow very fast. So it's not very scalable with respect to storage of commitments. So the extensions of the basic idea, the first extension is more efficient verification of commitment inclusion in the list of coin commitments. So now you don't need to sequentially scan all commitments on the ledger in order to verify if a given commitment is there. Instead, they use Merkle tree to organize all commitments, and then they could search for the following. I, the sender, know the secret such that commitment is a leaf in a Merkle tree with the given root. And that operation is much faster than sequentially going over the list of all commitments. Also, in the basic idea, I was only talking about coin ID, about coins, right? And the coin in the basic idea just have the same amount, 1 unit of cryptocurrency. So another extension is support for arbitrary denominations while obfuscating the amount. And yet another idea is the ability to convert minted coins back to Bitcoin. The system is very cryptographically involved, so the proofs of verification take many pages, so it would be difficult for me even to explain the intuition behind all the steps. I'm just giving you the overview. So that's what I wanted to say. I mean, this is just a brief overview of zero cash. Now, additionally, so now I'm switching away from zero cash and I'm talking about alternative mining. So let's take a look at a brief history of mining trends. Between 2009, when Bitcoin came out, and 2012, all mining was done on CPUs, essentially. Because Bitcoin was not so popular at the time, and the basic idea was to use CPUs in the beginning. And since there was not sufficient interest, people were not coming with the ideas how to do it more efficiently. However, in 2013, it was shown that application-specific integrated circuits, chips, called ASICs, can be much faster than CPUs and GPUs. So the mining based on them in Bitcoin, they would solve crypto puzzles much faster. And by that time, Bitcoin became popular, and there were many miners. There were also many rich miners who could afford to buy ASICs. Of course, ASICs are more expensive than CPUs and GPUs. So what happened is the following trend. Because of the price tag, the Bitcoin network was gradually taken over by wealthier individuals and players and enterprise-level mining farms. So you would have those huge mining farms, say in China, in Canada, certain provinces where the electricity is cheap. And all that resulted in a centralization of Bitcoin. So we previously discussed that fairness is a very important element and very desirable property of cryptocurrency. Well, this trend, due to use of ASICs, Bitcoin was losing some of decentralization and some of fairness. Okay, so what would be the solution? In 2016, the idea of equihash was proposed in an academic paper. In all fairness, they were not the first to consider such ideas, but they were the first to make it practical. So what was the idea? In crypto puzzles, you just need CPU, or you just need a computational unit. You can do computation on CPU, GPU, on ASICs, but you only need computational unit. What you need is to compute hashes, and fast. Hashes themselves do not take a lot of space. Even the inputs to hashes, in principle, they could be of arbitrary length, but in Bitcoin, they do not take a lot of space. Therefore, computing one hash is very fast, and computing many hashes just requires doesn't require a lot of resources apart from computation. what was changed in Equihash and other mining algorithms is to consider a problem where you would need not only computational units, but other resources as well. Okay, what other resources? A lot of memory and memory bandwidth, fast access to memory. And those are much more difficult to scale compared to computation. Because you cannot easily put many terabytes of memory in a single computer. So how did they do it? In Equihash was based like a practical memory-bound algorithm based on the generalized birthday problem. I'm not going to present the generalized birthday problem, in detail. But the idea is that you have like two matrices or two long vectors, and you need to find a pair of vectors whose multiplication would result, scalar multiplication would result in 0, for example. And we need to find all such different pairs. So it turns out that in order to do that, you need a sufficient amount of memory. And this is why, for example, the algorithm in Ethereum is different from crypto puzzles in Bitcoin. Again, with the same purpose of preventing decentralization. Or prevented centralization, sorry. Was it the end of the story? Does it mean that centralization didn't happen for Ethereum and for the others? Well, in around 2018, there came ASICs for Equihash. So they were doing much better than common purpose. But still, their improvement compared to normal computers was not nearly as large as improvement of ASICs compared to CPUs. And therefore, they exist, they are used, they are not as effective as ASICs in Bitcoin. And for this reason, decentralization in Ethereum is not considered as much of a problem as centralization in Bitcoin. And as a matter of fact, most of the mining in Ethereum today is done by GPUs. Not by CPUs, not by ASICs, but by GPUs. Okay, this is the end of this lecture. Again, it's just an overview of mining trends. Just to study the problem of Equihash would require at least one additional hour. So we decided against including the details in the course. But the paper is quite nicely written, and I recommend it to everyone. What is the view of the miner in a particular blockchain, sir?
What that block? What kind of function
block is a batch in transactions, right? Right. So again, in the lecture on Bitcoin, we talked about scalability of consensus and how much of a problem it is, and all different techniques that are used to improve the scalability. So one of the techniques is essentially, so imagine we have 100 transactions, right? So we can run a separate consensus on each transaction, or we can put them together in a single block and run consensus just once for the entire block. It turns out that running consensus one time is much cheaper than 100 times. So we are starting with the last lecture today, well, after which we'll still have a tutorial. In this lecture, we start the topic on Ethereum. So this is a topic that spans over 2 lectures. The second lecture will be tomorrow. So Ethereum is, of course, yet another cryptocurrency. However, it plays a special role because it's one of the most mature ones. It's also second after Bitcoin in terms of the market cap. So, and it also includes a lot of interesting technological elements, which is why we spend more significant time dedicated to that cryptocurrency. So I'll use quite a few different materials for the lecture today, but above all, I'll be using the paper called Understanding Blockchain Definitions, Architecture, Design, and System. So first, let's start from background on Ethereum. It's managed, well, Bitcoin is managed by Bitcoin Foundation. Ethereum is managed by Ethereum Foundation, but it includes, it's an industrial consortium, which includes many industrial players and enterprises such as Toyota and Microsoft. Its focus is on creating an open source and flexible platform. And of course, by platform, I'll soon explain what I mean by platform, as opposed to just cryptocurrency. The cryptocurrency it's using is 1 Ether. So is Ether, and 1 Ether is equal to e to the 18th of Wei. So Wei is a much smaller division of the Ether cryptocurrency. As of now, 1 Ether is equal to approximately 1863 US dollars. But of course it varies over the time. It came up with the idea of smart contracts and Ethereum virtual machine, which we will be covering. And it is permissionless. Initially, it was using proof of work, but later it switched to proof of stake. Later actually recently in 2022, so it was deployed in 2013, and from 2013, like 9 years of proof of work, from 2022, they switched to proof of stake. Ethereum, in addition, Ethereum has limited support for permissioned ledgers. So, in addition to the main public deployment of Ethereum, there are many proprietary deployments. So how did it all start? I was already covering this topic in the beginning. It started from a proliferation of Bitcoin spawn-offs. And then people are also, so why so many different spawn-offs? Because people realized that digital currency is not the only electronic object of value. So we could also store documents. Additionally, people wanted to support extended financial applications such as crowdfunding, which was not possible on Bitcoin. People wanted to support multiple party escrow transactions where there would be like one trusted party within the transaction only for that particular transaction. And in order to support that, there was a need to extend Bitcoin in a certain way. And as a result, we ended up with hundreds of Bitcoin spawn-offs. And then Ethereum envisioned that a single platform supporting all different extensions is better than 100 of specialized systems. So that's why we call Ethereum a platform, unlike Bitcoin. Okay, so what was the innovation in Ethereum? It provided a verifiable Turing-complete script language. As a matter of fact, it came up with the idea of Ethereum virtual machine. So it's like Java virtual machine for those of you who know Java. Every instruction in Ethereum is executed on a virtual machine. So every instruction may have the cost associated with it, it's all standardized. And no matter which operating system, no matter which client, every transaction consists of a set of instructions. It's like more or less like assembly code. And every instruction is executed on the same virtual machine, and it's verifiable. Okay, so additionally, of course, like virtual machine, instructions of virtual machine are in low-level language, right? So that's not the language in which we want to program. Therefore, there are many upper-level languages for developing smart contracts, and of course there is a compilation from the smart contract languages to the language of the virtual machine. And then Ethereum also provided templates for the scripts. Another interesting critical distinction from Bitcoin is that those scripts can be stateful, with the state stored on the chain, and significant amount of sophistication in Ethereum went into the question of how to store the state. And today we will be covering this question. And of course, later, as I was explaining in the lecture on the evolution of blockchain, the idea of this platform gave rise to distributed autonomic organizations and the application ecosystem of applications developed on top of Ethereum. So the analogy that Vitalik Buterin, who originally was the author behind Ethereum, was to use the Swiss knife analogy. It's a knife which you can see with so many different tools, but all combined within a single knife. So let's compare Bitcoin with Ethereum. So what are transactions in Bitcoin? It's just a transfer of Bitcoins. What a transaction in Ethereum is more complicated. In addition to transfer of Ether, we have a creation of smart contracts. We have internal transactions. We have specialized transactions for contract calls and so on. Regarding the accounts, other accounts in Bitcoin, no. There are additionally wallets which are like external to Bitcoin itself, but which are used in conjunction with Bitcoin. And okay, what about Ethereum? In Ethereum, there are accounts. There are two types of accounts. One type is accounts that belong to human users, and another type of account is account that belong to mechanized or rather automated smart contract. So each smart contract, a script in Ethereum, may have its own account, or even multiple accounts if you want. Transaction fees. In Bitcoin, the sender of a transaction decides how much fee to pay to the miner. In Ethereum, it works differently. First of all, Ethereum uses gas. So let's take one step back and let's talk about the concept of gas in Ethereum. So in Bitcoin, a script is just some very small program with the limited computation, and therefore use of resources by scripts, by executing those scripts in Bitcoin, is not a significant issue. In Ethereum, a smart contract or a script is like a full-fledged program. It may have loops. It may have functions, so one function calling another. So can you immediately see the challenge resulting from this? So what would be the challenge in Ethereum? If you start running full-fledged programs. Well, the question is who tests those programs, who debugs those programs? What if someone inadvertently or as an attack would write an infinite loop? So now every single node, so every single node needs to verify every single transaction. As a result, every single node will perform infinite loop. Like all nodes in the Ethereum network will spend significant amount of resources on that, right? So of course, like we need better scripts. Of course, we need better scripts. How do we make sure that the scripts are good? So the solution adopted in Ethereum was the concept of gas. Every script pays for its execution. How? Well, the scripts consist of instructions at the level of Ethereum virtual machine. So each instruction has an execution cost associated with it. And what happens is that every program in Ethereum has a budget for execution. And as the program is being executed, after each executed instruction, this budget is being decreased. And that happens until the budget reaches zero. If the execution finishes before budget reaches zero with a positive budget for the script, then the execution would be successful in that regard. If, however, the budget reaches zero even in the middle of the execution, then the execution would be immediately aborted. It's a problem of the script. So if someone wants to run the script to be successfully executed, that someone would need to provide sufficient budget for the script. And the budget is the gas. So one could say that while executing scripts are burning gas. Okay, so coming back to the question of the fees. In Ethereum, the fees are not specified by the sender. Instead, well, essentially there is no need for fees because the payment is for the execution of the transaction. And it's calculated based on the price of gas, right? So the price of gas may also vary over time. And it's calculated based on how many instructions were executed on the Ethereum virtual machine. So it's not specified beforehand. It's calculated after the execution. Block content. So what does a block consist of? Well, we already covered this question in Ethereum, in Bitcoin. In Bitcoin, there is a block header and there is a block body. And the block body is essentially a tree, or well, it's a list of transactions, which those transactions are organized in a Merkle tree. It's more complicated in Ethereum, mostly because we need to store the state. So in Ethereum, there is a transaction tree, which is pretty much similar to the transaction tree. However, there is also root hash. There is also like a tree for the state, and there is also a tree for the receipts. I'm going to take take a dive and speak about both the state and the receipts soon. Okay, next, what is the state in Bitcoin? So in Bitcoin, we need to keep track of unspent TXOs, right? In Ethereum, we need more. We need to keep track of the accounts, both user accounts and public accounts. We need to keep track of the receipts, and the scripts are also like a program, so we need to sure that those programs have not been tampered with, right? So there could be some significant code involved. Querying the ledger. So in Bitcoin, the main purpose of querying the ledger, either you download the ledger and verify all of it, or you verify inclusion of a transaction, which is simple for a full node, but which takes the simple payment verification procedure for the lightweight nodes, which only keep the headers. Ethereum. In Ethereum, querying is much more sophisticated. So we can ask for the balance of a particular account. We can ask for local proof for events, transactions, and more. So this gives you, like, I have not given you details, I'm going to go deeper, but this gives you an overview of how Ethereum was advancing the field compared to Bitcoin. So what are the new conceptual elements in Ethereum? When Ethereum was using POW, it was using a different mining algorithm to prevent ASICs. It's not relevant so much now after Ethereum switched to proof of stake, but to date, Ethereum switched to validators and proof of stake. As mentioned, Ethereum came up with the idea of smart contracts. Well, okay, it's exactly true. With the idea of smart contracts was again from the 90s, but Ethereum was the system which came up with the idea of integrating smart contracts within the blockchain. And by the way, smart contracts, so I was talking about gas. I mentioned, like, you pay for the execution of instructions. That's true. Well, you additionally keep for storage. You additionally pay for storage. So there is another element of payment in Ethereum. Like, you store, the smart contract stores information, it needs to pay for the storage. So Ethereum is not using UTXO at all. It doesn't have the idea of those individual tokens with values. Like Monero does, Bitcoin does, not Ethereum. Ethereum has balance like a bank. So for example, Alice receives 10 different transfers. All those transfers would not be kept separately. They would be consolidated in a single account that belongs to Alice. Okay, more. So please remind me which consensus rule is or conflict resolution rule is used in Bitcoin. We talked about it in the lecture on Bitcoin. So what's the name of the rule that's used to resolve conflicts and reach consensus in Bitcoin? If we have several branches competing with each other, how did we select the best branch? The winning branch. Please speak up. With the longest. So we were selecting the longest branch. That's the rule in Bitcoin. Ethereum uses a different rule, and there is a good reason for that. The rule in Ethereum is called the LMD ghost rule, and using this rule, Ethereum is able to provide faster transaction confirmations. So we are going to talk about the differences, of course. And of course, as mentioned, Ethereum uses different storage solutions, including state storage, but there are also other significant differences with regard to how the data is stored on Ethereum compared to Bitcoin. All right, so Let's go over different elements. Transactions in Ethereum. This is how transactions and blocks in Ethereum look. So this includes block header, or similar to body, transactions. However, the transaction it includes the gas price. Gas price is like how much the sender of the transaction is willing to pay for the gas, because as mentioned, the gas price is also variable, and there is negotiation about the price of the gas. If the same transaction is executed at different times, like in a year from now, I'll be issuing same transfer, I may be paying different amount for the gas. So price is how much the transaction is willing to pay for the gas, for the unit of gas. There is a recipient. So Ethereum does not care about traceability. It just puts the recipient. Now we have account, so it can put the target account of the transfer inside the transactional structure. Of course, the amount, signature, so that's the same, but it also has some interesting different fields like account nonce, which has nothing to do with the nonce of POW. It's something used to verify the account. Let's talk about proof of stake and validation of blocks in Ethereum. So every node in Ethereum can become a validator by staking certain amount of Ether. Now, the assignment of validators and block proposers is done on the per epoch basis. So Ethereum divides time into epochs of time, where each epoch takes 6.4 minutes. And each epoch is further divided into time slots. Specifically, so 6.4 minutes are divided into 32 slots, 12 seconds each. And the validators and block proposals are selected on a per slot basis. And the way it's done is again using a pseudo-random assignment. One validator becomes an appointed block proposal, while the other validators for a given slot become attesters, so they verify the correctness of the proposal. And the assignment is such that all validators are designated to serve as attesters exactly once per epoch, not per slot, per epoch. And all attesters are assigned to a given slot, are split up into many equal-sized committees. So there is a rule to have minimum 128 attesters in each committee, and minimum 164 committees per slot. Minimum 1 committee per slot, maximum 64 committees per slot. So thanks to these rules, we can calculate the minimum of validators required for Ethereum to operate. So we need to have minimum 1 committee per slot, and we need to have minimum of 128 attesters in each committee, which means that we need to have and then we have 32 slots for each epoch. So attesters are never used within the same epoch, and therefore we require a minimum of 128 times 32 equal to 4096 validators. The same validators can be reused across different slots. So for the next slot, we could use the same set of validators, or we could use different validators. But within, for a different epoch. But within the epoch, we are not allowed to reuse attesters. Okay, so what's the situation today? Today, instead of the minimum of 4,000 validators, we have over 1 million validators. So it's not about the minimum, it's about the maximum. The maximum of 64 committees has already been reached. In addition to validators, we have aggregators. Aggregators are validators that have some additional duties. Namely, they participate in the dissemination of the blocks. So those are the rules about the committees and proof of stake in Ethereum. So again, one could say, so why would anyone want to become a validator? So the proposal, the block proposer gets a reward similar to the reward in Bitcoin. The validators also get some smaller rewards. So this is why everyone wants to become an official validator, official attester. And of course, like everyone else, apart from the official attesters, can also validate the ledger. The ledger is open to all. The attesters do not get any significant additional information about the ledger, but they get a reward for officially attesting the blocks. So the switch from POW to POS in 2022 significantly reduced energy consumption, also reduced transaction fees and cost of gas, because now it's cheaper to execute transactions. There was a fear of increased centralization, because now, of course, like not everyone gets to become a validator. You need to stake some amount. And there was a fear that basically only a selected few participants, nodes in Ethereum, could become validators. And that would result in a centralization. So far, as you can see, there is over 1 million validator nodes. So that's good, in the sense that the centralization fears did not come to be supported in reality. Okay, so that was about POS and validation. Now, as I promised, the conflict resolution in Ethereum was different compared to Bitcoin. So instead of the longest branch, we are selecting the heaviest branch. What do I mean by that? So here you can see branching in Ethereum. Well, in the past, here it's vertical. It starts from Genesis at height 1, block at height 2. Start with the branching. Two alternative versions at height 3. And here, like on this version of block 3, we have 3 different versions of block 4. Under this version of block 3, we have just one version of block 4. But at height 5, here we have repeated versions. So we have nested branching. Okay, so how do we select the winning branch? The longest branch is clearly this one, right? It's not the winning branch. So in order to select the winning branch, we compute the amount of blocks under a given branch. So the amount of blocks, the amount of also the amount of transactions. So here we have, here it's 1. This one combines with 2, 1 plus 2, 3. still free. Here we have like 3, because there are 3 transactions here. Here we have 5. This one is 5 plus 3, 8. So we calculate the weights based on the amount of later blocks. And then we select, if there is a branch, we select the version of the block with the biggest weight. So here is this one with the biggest weight. And then we have several alternatives here. We select the one with the biggest weight, choose 3. Not the longest one. So it has been shown, okay, so what's the big idea? Why do we want to do that? Because this way, the winning branch is secured by high amount of, the same idea, by the way, is applicable both to proof of work and proof of stake. So it was the same idea. And the idea is that the winning block is secured by high amount of work or high amount of stake. So it's more difficult. It's more difficult for the attacker to overcome the weight than it is to overcome. So in case of branching, the main chain is secured by a high percentage of blocks, which is also called the mining utilization, the metric which we looked at when studying Bitcoin energy. The mining utilization is high in Ethereum compared to Bitcoin. Go ahead. Good question. In this case, yeah, in this case, we may select. Okay, so usually, I mean, it's the same question you could ask about Bitcoin. What happens if 2 branches have the same length? Okay, but we consider that question indirectly in the context of Bitcoin. So what would be the answer in the context of Bitcoin? What happens if 2 branches have the same length? Exactly. Exactly. It's a transient answer. It's a transient situation. It's only a temporary situation. If we have 2 competing branches with the same length, then there was a slide about that. Some nodes would continue mining on top of one branch. Some nodes would continue mining on top of the other branch. So eventually, because of the variance, one branch would be extended faster than the other branch. And the symmetry will break. And the same true. Okay, so in fact, like this idea of the okay, like why is it called Ghost? It came from the Ghost protocol, and the Ghost protocol is actually quite relatively old. It's also from 2013. So the idea of using this conflict resolution rule is something Ethereum came up with from the beginning. It's not new due to the proof of stake. But the same concept is also applicable to the new Ethereum using proof of stake. So as a result, Ethereum is more secure than Bitcoin if we assume the other like the same configuration parameters. However, they are not the same. Thanks to higher security and the ability to tolerate branching better, Ethereum reduced the average time to produce a block. So in Bitcoin it's 10 minutes. In Ethereum it's about 13 seconds. And of course with 13 seconds Ethereum gets much more branching than Bitcoin with 10 seconds. But it's able to tolerate branching better. Okay, so this was about the conflict resolution role. The next question we are going to consider is that of blockchain storage and its organization. So in Ethereum, we have a chain of blocks which is stored in files on disk, but additionally the storage includes a key value store for keeping auxiliary information related, for example, to the system state. And with emphasis on the state storage and state-related operations, such as we can search for the state, this emphasis results in more complex storage mechanisms compared to Bitcoin. So the balance of roles between the chain of blocks and the key value store is fundamentally different in Bitcoin and in Ethereum. In Bitcoin, we never search for we never need to search for specific bits of information. And if we need to search for blocks, it's conducted mostly using the chain and not the key value store. While in Ethereum, the reverse is true. In Ethereum, all information that is stored in files on disk is also duplicated in the level DB key value store. For example, we keep block headers and transactions in level DB key value store. And the key value store is the main storage element used in the search. So the storage on disk of individual blocks on disk is not as important in Ethereum as it is in Bitcoin. And another significant difference is that Ethereum doesn't use Merkle trees. It uses a modified version called Merkle-Patricia trees. Why? Because that kind of structure is also good for Merkle tree is only good for cryptographic verification. It's not used for searching. But Merkle-Patricia tree is also used for searching. So here's an illustration, right? So we have a block, which is also, and we also have the database. So in the block, we have proof of work or proof of stake related information. We have, like in the header, we also have the hash pointer, the secure pointer to the previous block. That's the same. But then we have different trees. We have transaction tree, which is similar to Bitcoin, but we also have state tree, and we also have receipt tree. So now it's probably a good time to, okay, so transaction tree contains all transactions in the block structure as Merkle tree, so the same, but there is some including, for example, the gas price. Then we have a tree, Merkle-Patricia tree, for storing the state after all transactions are set, and we calculate the root hash and we store the root hash also in the header. We have a third tree, which is a receipt tree. What are receipts? We log out the outcome of each transaction, and we sign the outcome, the output of each transaction. And that is like the receipt. The receipt shows, yes, I have executed the transaction, and this is the output of the transaction. So those receipts are also verifiable, stored, and they can be verified in Ethereum. So let's talk about Patricia trees. Unlike fixed transaction history, the state in Ethereum is frequently changed because new accounts are inserted and old accounts are deleted all the time. So we need to maintain the state. And additionally, the state of an account needs to be searched. So the Merkle-Patricia tree is the structure which can support all those operations because it provides logarithmic complexity for search, for insertion of new data, for updating the data, and for deleting the data. In addition to efficiently constructing Merkle proof. So similar to the Merkle tree, data items are stored in the leaves. However, unlike Merkle tree, Merkle-Patricia tree is a prefix tree, which uses hashing mechanism to produce a key string that determines the path of the data item within the tree. And in Ethereum, the key is encoded as a hexadecimal, so the vertex has a number of children which doesn't exceed 16. Let's take a look at an illustration. Imagine that we have two data items. For example, two transactions or two state elements, two accounts. And imagine that one data item is hashed to the value of ABCD, and the other data item is hashed to the value of ABEF. So, what is a prefix tree? In a prefix tree, we'll be building a tree based on those values. So ABCD and ABCD, and then in the leaf we'll store the item which hashes to ABCD. And then ABEF, and in the leaf we'll store the item which hashes to ABEF. Okay? So this is how the prefix tree would look. Now, Merkle-Patricia tree is a classification called the compact predict tree. So instead of having many levels, the tree will be compacted to A node, and then CD node, and EF node. So it's the same case, but different representation, more compacted. And this is the one, the compact predict tree is the one used in Ethereum. And it's used for pretty much everything, like accounts, balances, and so on, as we'll see soon. So the trees are stored in a database as mentioned. Each vertex of every Ethereum tree is stored as a separate record in the level DB storage, which is again a key value storage, and the record key is derived from the hash. Additionally, the key of the record is stored in the parent vertex node. Then the hash of the root vertex is stored in block header as mentioned, and used as a starting point for the search, for finding other tree vertices in the database, which allows for an efficient traversal of the entire tree. So in order to find data item which is in the leaf of the Merkle-Patricia tree, we start from the hash root, and then we go to the database, and at each level of the tree we find the right node, which should be like another entry, another record in the database. So the traversal would need to look at the number of entries, which is the height of the tree. Now we have state tree and the storage tree, and I'm going to talk about both. So in the state tree, each leaf corresponds to an account in Ethereum. And the key string for the account is derived from the hash of the account address, while the value of the leaf includes the balance and the root hash for the storage tree of the account. So why do we need two trees and two levels? Because the first level is different accounts, and the second level is how we represent the data, the state of one particular account. For the storage tree, which is the tree for representing the data of one particular account, each leaf represents Ethereum data for a given account or a given contract. And the key string is derived again by the hash of the contract address, while the values reflect the data model described in the Ethereum contract. And an updated state of an Ethereum account is retrievable by traversing the storage tree vertices in the level DB database. So let's take a look at the visual representation. So these are blocks stored on a file. And this is a header in the usual. And then block body with transactions. Okay, so this header is stored in the database, key value store. And the body but separately. Okay. Now, these are records corresponding to one node in a tree. Node in a tree. So, state tree. We start from the state root hash. Now we want to find the right account, the entry, the record in the database that corresponds to the right account. So we do the traversal. We start from the root hash, which points to the record in the database. And then point in the database would point to a branch hash, right? So like the hash of one of the branches. So this is how we find the right branch. And then from the branch, we go to the leaf, right? So there are two leaves. In our corresponding to two different accounts. Now, the leaf record in the database corresponds to one account, and it stores the hash, the root hash for the storage tree. So now from the state tree we can start traversing the storage tree. And the storage tree would be would start from the root hash, and would similarly go to one of the branches, and then we have the leaves. And in the leaves we have some specific information related to the storage of data in that particular account. And similarly, we have a tree for receipts, and we also have a tree for transactions. Okay, so here you see a different representation, but it's similar. Maybe it's easier to understand this way. That's here we have state Merkle-Patricia tree. And here we see the tree itself, where each node, each node or each vertex in the tree is a separate record in the database. And see the balance. We can retrieve the root hash for the storage, which points to the root of the storage Merkle, by which we can also traverse and get to the root. And in the leaf, we can find individual variables. So imagine you are writing a program, particular smart contract, and the program includes several variables. So we have each of the variables, and each of the variables can be updated over time because it's part of the state. Okay, so that program would be deployed for a particular account. So in order to fetch and update the value of the variable in the program, we need first to find the right account by traversing the state tree. And then we need to find the right variable for that account by traversing the storage tree. And once we find the right variable, we can retrieve its value and update the record or the record in the database. Now, Ethereum, okay, so that's the view for one block, and that's a view for a different block, right? So how does it work in Ethereum? In the sense that, okay, suppose we have two different blocks, and the state has changed from one block to the other, but not everything in the state has changed. Just some of the variables in some of the accounts have changed. So does Ethereum need to replicate everything for the new block? Even the records that have not been updated? The answer is no. Ethereum is applying very smart copy on write technique in order to save on the space. So how does Ethereum do that? If the same account has not been changed from the old block to the new block, then what happens is that the pointer in the new block would still point to, like here, like in this example. You can see that there is a pointer from the vertex in the Merkle tree, the new block, which points to the vertex in the old block. Right? So you can see 2 points point to the same vertex. This vertex has not been updated between the blocks. On the other hand, this account has been updated. And as soon as it's updated, only then the new record is created for the new value of the data in the account. And the same technique, copy on write, is also used for the storage of partition. So here you can see that one variable, it has the same value in the old block, then the record for the variable would not be duplicated. But the variable 2 has been changed. Then a new copy of the record, the new value. And what happens now is that not only are we able to answer the question, what's the state of the most recent block, but we can go back to history and know the state for each of the blocks in the past. So we take some historic block and we can restore the state of that particular block even today. So it's relatively expensive, but because of this optimization, copy on write, it becomes much cheaper. So that's the last slide in the first lecture on Ethereum. The second lecture would be dedicated to smart contracts. And as usual, questions are welcome. Thank you. Slide number 14. Yep.
Here you said that the old accounts are deleted. And even the third point, deletion is possible.
Yes.
So when you delete, you are tampering the data, right? So how would
I am not, well, so when I say deleted, there is a transaction which deletes the account. So instead of eliminating the data, I add the transaction which says now this account is inactive.
I'm not getting the deletion means you are adding.
It's a deletion of an account. Imagine like, okay, you open an account in the bank, and then you close the account in the bank. So now the account is inaccessible to anyone, including you. However, the bank still keeps the record of the account. The bank knows that the account was first opened and then closed. The same here. A ledger is a log of all transactions. So in the ledger, people would be able to see this account was opened, created, and then this account was deleted. So we do not delete information from the ledger. We just make the account inactive. Of course. I understand. So you still, like, the ledger is still